Welcome to today's Explainer. We're jumping right into the fascinating architecture behind multi-agent systems, diving into Michael Albada's book, Building Applications with AI Agents. We're moving way past those simple chatbots you might be used to playing around with, and we're looking at how real, complex AI systems are actually engineered to get work done. So let's start with a core dilemma. A single generative AI model, it's incredibly powerful, for sure. But what exactly do you do when a problem requires multiple tools, complex planning, and, long-term memory? You really can't just throw an entire business operation into a single prompt window and cross your fingers. Here is our roadmap for today. We'll be covering the limits of single agents, orchestration, semantic memory, building multi-agent teams, and finally, coordination types. Section 1. The limits of single agents and what happens when one agent fails. To really grasp the bottlenecks here, think about this. A basic chatbot is great for structured FAQs, right? But it literally shatters when it faces novel, unstructured inputs that require dynamic, multi-step planning. Picture a customer support center. If someone asks for a tracking number, a simple workflow handles it perfectly. But what if a customer emails saying, hey, my laptop battery is swelling and looks like it might explode? An open-ended, potentially dangerous situation like that absolutely breaks rigid, rule-based systems. You need an agent that can dynamically parse intent, consult a knowledge base, draft a response, and immediately escalate to a human. Section 2. Orchestration. The system's brain. To solve those limitations, we introduce a central orchestrator. Think of this orchestrator sitting right at the center of the system as the CEO. It takes your user query and routes it to external tools, local tools, and databases. Instead of just blurting out generated text immediately, it coordinates. It decides, hey, do I need to look up data in an external API or trigger a local function, all before it ever relies on the foundation model to synthesize an answer. It's a highly active task manager. Because the orchestrator is handling these execution loops, things like fetching logs or querying APIs, human roles completely shift. As Michael Albada points out, this evolution transforms human roles from task executors to task managers. You're no longer writing the email or pulling the database record yourself. You're managing the agent that's doing it for you. Section 3. Semantic memory and vector stores. Okay, so we have a brain, but now we need to give that brain a path to draw from, right? If the orchestrator is the CEO, well, it needs a filing cabinet. Unlike a traditional phone book that uses keyword search, where you literally have to type the exact word to get a match, semantic memory uses vector stores to understand concepts and meanings. It projects text into a dense, high-dimensional numeric representation. This means if you search for the word puppy, the system knows to pull up information about dogs, even if the exact word puppy isn't explicitly used anywhere in the text. To actually create this memory, documents are first broken down into smaller chunks. Then, they're passed through a neural network called an embedding model to create numerical embeddings. These continuous arrays of numbers are finally stored in the vector database. It's essentially a pipeline that transforms your company's messy, unstructured data into a semantically searchable brain. Pretty cool, right? Now, when an agent needs to recall this information, it uses a 4-step process known as Retrieval Augmented Generation, or RAG. It doesn't just blindly guess the answer from its pre-training, it actively retrieves the facts first. In action, this RAG workflow kicks off when the user's question goes directly to the controller. The controller queries that vector knowledge store we just talked about. It grabs the most relevant semantic memory, the specific chunks of text that answer the query, and then, and only then, passes both the user's question and the retrieved information down to the generative foundation model to synthesize a final response. This is absolutely crucial because it keeps the agent grounded in your actual data, which drastically reduces hallucinations. Section 4. Building a multi-agent team and scaling up capabilities. Once we actually have a smart, memory-equipped agent, how do we scale it up to handle incredibly complex workloads? Well, the key here is divide and conquer. By dividing labor, specialized agents can work together seamlessly. Let's look at a supply chain, for example. If you have one single agent trying to manage 16 different tools, checking inventory, routing trucks, messaging suppliers, it's going to get overwhelmed and fail. But if you break that down into a multi-agent system, you can have one specialized agent exclusively for inventory, another just for logistics, and a third for supplier relations. This division of labor brings massive, massive advantages. It prevents tool overload for a single model and allows tasks to run in parallel. The inventory agent can be scaling warehouse operations, while the logistics agent is rerouting a truck around a storm, and the supplier agent is reordering parts, all happening at the exact same time.
Plus, it adds crucial redundancy, meaning if one agent's API connection suddenly goes down, the entire supply chain system doesn't necessarily crash. Section 5. Coordination types. Democratic versus hierarchical. So how do these networks actually govern themselves and make decisions? Because without coordination, you just have chaos. There are some massive trade-offs between two major coordination styles. In democratic coordination, every agent has an equal vote. It's incredibly robust with no single point of failure, which is great for something like a distributed sensor network. But honestly, it's agonizingly slow because agents constantly have to message each other to reach a consensus. On the flip side, hierarchical coordination organizes agents into tiers, kind of like a military operation. It's highly scalable and execution is streamlined, but passing messages up and down that chain of command introduces communication latency, and the design itself is highly complex to build. Now, there is also a very popular middle ground known as manager coordination. This is where one central supervisor agent analyzes the user's request and routes tasks to subordinate specialist agents. It lowers the communication overhead drastically because the subordinates just talk to the manager, not to each other. However, you really have to be careful here because that manager agent now becomes a critical single point of failure for the whole system. Whatever structure you end up choosing, you absolutely must monitor these complex interactions. As Albada points out, monitoring is how you learn. In multi-agent systems, agents can sometimes get caught in unintended feedback loops, triggering conflicting actions in one another. So you need robust observability to catch those loops and optimize performance. Ultimately, as we scale these autonomous networks from simple personal assistants up to massive enterprise-wide multi-agent teams, our role as humans shifts entirely. We stop executing tasks. We'll spend some time reviewing agent outputs, sure, but eventually our primary job becomes governance, defining policy boundaries, maintaining role-based access controls, and auditing the systemic behavior of our AI teams. It's a profound shift in how work gets done. We are rapidly moving from a world where we use software as a tool to a world where we manage software as a team, which leaves us with a critical question to consider. As AI agents become autonomous teams, are you ready to become their governor? Thanks for joining me on this explainer today. Keep learning, and I'll catch you next time.